Okay, I'm going to make a couple of quickie videos to go over the basics of statistics that we need to know well in order to proceed into the advanced statistics. So I believe the first thing we started with was the graphs. Graphs are also called frequency distributions. It shows you how your data is kind of spread out, which is important in statistics. Okay, that's what the science is all based on is where the data is laying. Okay. First thing was the pie chart. Pie charts are good for showing what part of the whole something is. So, like with our example with the library books, if let's say you had 10,000 library books, you can look right off the bat here and say that over 25% of them are adventure and romance novels. So that's what pie charts are good for. They're good for showing parts out of the whole. And then next up is a bar graph. A bar graph is best used for comparing one entity, one value, one category to other categories. So looking at this, you can see it in the blink of an eye that the most important or the largest selling color of car is a silver, right? It's way up there. Bam. And black is number two, and then brown is the last one. That's what bar charts are good for. Okay. You can instantly see who the most popular is here. It's Tuesday, and the least popular is Monday. That's what bar charts do for you. Important. The next few graphs are going to show us how to check for normality of data. Normality is the number one assumption for almost every test that we're going to do in this class. So your data has to be normal. Stem and leaf plots, they show you how your data is distributed. And if you look at it this way, it's kind of hard to tell if it's skewed or not, but let me show you a trick. So there's a stem and leaf plot. It's you really can't tell if it's skewed or not until you turn it on its side. And looking at it now, you could see, right? If you trace the line over these last numbers, you could see that it was not very normal. In fact, this is skewed to the right. Okay, so that's a stem and leaf plot. Box plot. Again, this is very skewed data, right? You got way too much of it in this first quarter here. And here's another box plot. This is relatively normal because the T above the box and below the box, they're relatively the same. They're not perfect. They don't have to be perfect, but this is less skewed than the other one for sure. And then here's your money, the histogram. The difference between a histogram and a bar graph is you'll notice that the x-axis is in interval units. So that's the histogram. The x-axis has values that increase. Da, 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 da. And then your y-axis is the number of things, whatever you're measuring, in that specific interval range. So as your interval range, it's the values down here on the x-axis get thinner and thinner and thinner. A normal set of data, if you just connected the top of these little boxes, would turn into the bell curve. And this is a very important tool used in statistics. Most of everything that we're going to do based on null hypothesis testing will be based on this little curve here. And this, again, is called the standardized normal distribution curve, frequency curve, the bell curve. It goes by many names. But this is what we're going to be using a lot of in our search for statistics knowledge. The measures of central tendencies. In other words, what's going on with most of the data. Okay. The mean, pretty basic. You guys probably know how to do that since the 7th grade or something. But we're talking about the arithmetic mean. There are other means, but in statistics, we're just using the arithmetic mean. And the median and the mode. In a normal distribution, the mean should be pretty close to the same number as the median and the mode, okay? And variance, very important in the rest of this semester. Variance is how spread out your data is away from the mean. So we have to be careful. A mean can either be a good representative of the data. In other words, most of the other data is really close to the mean. That gives you a strong mean. But a lot of times you can have data that's all over the place and still come up with a mean, but that mean is not a good representation of the data. An example of that is pretend you had a bucket of ice water and a bucket of boiling water. The average temperature there is somewhere around 75 degrees, which is pretty comfortable. But if you stuck a foot in each one, you would lose both feet. Okay, so it's my way of teaching. A strong mean is where data is really close to the mean, and a weak mean is where the data is spread all over the place, and we use variance to determine that. It's a mathematical formula, right? If a set of data has a big variance, that means the data is far away from the mean. If it has a small variance, that means it's close to the mean. And we measure that, we standardize the distance from away from the mean, and we call that a standard deviation. So the standard deviation is the square root of the variance mathematically, but they both are very important and tell us on average how far the data is away from that group's mean. Okay? An outlier, that's something that's way out there. Suppose you took 10 people at random and you found their annual salaries, but one of the guys was Brad Pitt. Okay, so he makes $1 billion a year. So if you took that average of those 10 people, including Brad, you would get an average annual salary of, $99 million a year, which is not true. Okay, so that's why we tend to get rid of outliers. Quartiles, that allows us to split the data up into force. That's kind of how we use the box plot. And we use the 5-number summary to build a box plot. So that's what these central measures of central tendency are. But the main thing is the mean. Is it a good mean or a bad mean? And you kind of can tell by how big the variance is and how large the standard deviation is. Last thing is, if you get a set of data where your standard deviation is greater than your mean, you're in trouble. You got a seriously skewed set of data. So that's it for this part. Okay, next chapter. Normal distributions and z-scores. This is probably where it gets real crazy for you guys. Z-scores are standardized scores using a formula that are then charted on a distribution curve. And if the data is normal, you'll get a normal distribution curve. And that's what we kind of need in order to proceed with these data analyses. But a density curve basically is just any kind of data, the way the data falls. Okay, it's not necessarily normal until you've actually made it. Okay, you don't know if it's normal until you've plotted it or something. So normal distribution curve, I think you know what that is. The empirical rule, bam. I had a young lady in a class that all she basically did was remember the empirical rule, and she got a B+ in the class. Because the empirical rule is literally at the base of all our decisions when we start making our null hypothesis testing. Okay, let me try to show you how that works real quick. The empirical rule states that 68% of your data should fall between 1 standard deviation above the mean and 1 standard deviation below the mean. In other words, 2/3 of your data in a normal data set will be between -1 standard deviations and +1 standard deviations after all the data in the data set has been standardized. Okay, that's how that works. But the number one thing is the 95% group. This rule, the empirical rule, states that 95% of your data is going to fall between -2 standard deviations and +2 standard deviations between the mean. So we use that 95% figure a lot. We're going to use that to whether to reject or not the null hypothesis. But the flip side to that is, so 95% of your data should fall between -2 and +2 standard deviations of the mean, but that means there's 5%. We should expect extreme values. In every data set, there should be some extreme values, 5% worth anyway. Okay, so that's part of the normal data set, is to have a couple of items that are on the extremes, either way out here or way to the other side. Okay, so remember that rule. 95% of the data should be within plus or minus 2 standard deviations. That number 2 is going to come back again and again and again. So here's the standardized formula, right? Your z-score, it is literally the number of standard deviations away from the mean each individual piece of data is. But you take the individual piece of data, you subtract it from the group mean, you divide it by the group standard deviation, and that standardizes all your data. And that's what we will do in statistics from now on. Actually, the software is going to do it for us, so we don't have to worry. And again, you know what a standard normal distribution looks like. That's the bell curve. And a z-table, takes a little practice getting used to. Let me see if I can't pull one up real quick. So let's pretend we take a z-score of 1.12. Okay, so there, the 1.1 is right here, and the 0.02 is right here. So 1.12 would give us an area under the curve of 0.8686. What that literally means is, for a z-score of 1.12, it would eat up 86% of the area underneath this. In other words, 86% of the rest of your data should have a z-score of less than 1.12. Less than. That's important. That's what these numbers all represent. It's the area to the left of the z-score that you're looking up. So if you wanted to find something greater than that, you would take the area number that's here and you would subtract it from 1. So the probability that you're going to pull a piece of data that's less than 1.12 standardized score, z-score, is going to be roughly 86%. The probability of picking a piece of data that is greater than 1.12 would be 1 minus 86%, or roughly about 14%. That's how that works. I know it's very confusing, but again, we're going to let the software do this for us. So that's it for z-scores and frequency sampling distributions. What that means is that all of our data is going to be coming from a sample. You will never get the entire population. Example, you want to find the average height of every 32-year-old male. You're not going to go around the world and measure every 32-year-old male there is. No, you're going to try to grab a convenient sample size somewhere of 32-year-olds and measure them and use that. So that's a sample. So the main thing that you need to know here is that samples have statistics. Any piece of information from a sample is called a statistic. So that's the mean, the standard deviation, the variance, that kind of calculated information from a sample is called a statistic. That's the name of the course. Any piece of information from a population is called a parameter. Again, they can be a mean, a standard deviation, a variance, but if the data you're pulling it from is the entire group possible, that's called a parameter, okay? So that's the main thing you need to know about that. And with sampling, we have a basic rule. The law of large numbers states that, the bigger the sample size, the more accurate your data is going to be. Again, with the sampling distribution, there is one major thing that you have to know, and that's when you... Hold on again. Let me rearrange this picture here. There it is. So if you remember the original z-score, it was just the individual minus the mean divided by the standard deviation. But now you're talking about a sampling distribution. You're comparing the sample mean to the stated population mean divided by the stated population standard deviation divided by the square root of the sample size. So what this does is it's going to reduce your possibilities, okay? What this does is it makes your denominator different than a regular z-score. So whenever you're taking anything from a sample, you have to divide your standard deviation by the square root of the sample size. This denominator is also known as the standard error. So a standard deviation is from a population, a standard error is from a sample. So that's the big parts of this chapter. Moving on. Confidence intervals. We're almost done here. But confidence intervals, very important indeed. So confidence interval is where we try to use information from a sample to try to trap the true population mean. Okay, so we're using a sample mean to try to determine a true population mean. So that's what a confidence interval does. We try to, it's a plus or minus factor from our sample mean. Okay, there's a couple of conditions that have to be met first before you can do the confidence interval. Okay, so I'm not going to go over that. You can read it over yourself. But confidence level tells us what size confidence interval. They're not exactly the same thing, but they are very, very strongly related. So confidence level, let me rearrange the frame here. So if we have a confidence level of 95%, which should be ringing your bells from the empirical rule, right? That basically says that the critical value z, which is how many standard deviations away from the mean it is, it should be, the empirical rule said 2, right? 95% of your data, according to the empirical rule, in a normal distribution is plus or minus 2 standard deviations. And look how close this is to 2, right? It's 1.96. So that, again, is the 2 standard deviations plus or minus the mean should contain about 95% of your data. So that's what a confidence interval is. And not to give it away or nothing, but we're going to use the confidence interval to reject or not reject the null hypothesis, okay? So, but let's keep going. So the margin of error, again, is the plus or minus factor to your sample mean. So that sets the interval of where you're hoping to capture the true population mean, okay? So, and that's confidence interval. And a sample size, your sample size has to be the right size, or your confidence interval will be useless. Now, there's a way to calculate sample size by hand, but in this semester, we're going to learn something called power. And power is directly related to sample size, but it all goes back to the law of large numbers, right? The bigger the sample size, the better the study. That's all that means, okay? All right, so that's it for confidence intervals. Coming up next, the null hypothesis. That's what significance testing is you're just trying to shoot down the null hypothesis. The null hypothesis basically always states the same thing, right? That there is no difference anywhere between any groups. Everybody's exactly the same. So we use statistics to either reject that statement or not. So, but when we start out early, we are testing a claim, right? Let's say the National Football League says that the average football player weighs 232 pounds, something like that. So our original null hypothesis would equal, right, that the mean equals 232 pounds. And then we would try to either prove that or reject that using statistics, okay? But that's what we're going to do with tests of significance. And, well, in a nutshell, the test itself is an algorithm where we find the sample mean, we compare it to the other mean. It might be a population mean, it might be another sample mean from a different sample, but we're going to look at the difference between those two means, right? So if you're looking at the difference between two means, the null would state that they're going to be exactly the same number, right? So we're going to try to shoot down that null and that's why, I want you guys to practice this over and over again. But here's the formula. You go ahead and calculate the differences between the mean. You divide it by the number of standard errors. That will give you a z-score. That will tell you how many standard deviations away from the mean your individual sample size was. If it's too far away from the mean, you get to reject the null. and that number is 2. In other words, if your z-score or t-score is greater than 2, you get to reject the null, because what happened is it did not fall within that 95% confidence interval. So it's the same thing, but it's working backwards, okay? And again, this is going to take practice. But a p-value is the probability value, which is the same thing as the area under the z-curve, that normal bell curve, okay? So the p-value is the area under the curve. If your p-value, which is generated by your z-score or your t-score, if the area is very, very small, that means that the null is probably not true, okay? And the critical cutoff is if your p-value is less than 0.05, unless otherwise stated. You can have lower p-values, but at this stage of the game, we're just going to use 0.05, okay? So another way to think about a p-value is the p-value stands for the probability that the null is true. So if you have a very small p-value, that means that it's not very probable that the null is true, okay? Another thing that I want you to remember is a large test statistic. In other words, a large z-score or a large t-score is going to generate a small p-value. And here's your magic word, significance. Significance literally means that somebody did some math on this stuff somewhere. I'll say it again. Significance means that the numbers were crunched through all these formulas. They got a big test statistic which produced a small p-value. If that process did, in fact, produce a small p-value, smaller than 0.05, you get to say that there is a significant difference in there, or that your data has significance. Again, the word significant means that somebody did some math to it somewhere and they proved it, okay? Type 1, type 2 errors. Now, these are not errors made by the researcher. It's not like you made a math problem like you added when you subtracted or something like that. That's not what these are. An example of a type 1 error, that's where you reject the null when you should not have. Let's go back to our 5'9", 32-year-olds. Let's say that you picked 30 people at random and you measured them and you came up with an average height of 6'5". It just so happens that the sample that you picked were all Yugoslavian basketball players. It's not very likely, but it could happen. So when you get a type 1 error, it's nothing the researcher did wrong. It's just that your sample was for somehow they were all from one extreme range and they gave you a false result. That's a type 1 error. And that's when you reject the null when you're not supposed to. A type 2 error is just the opposite. So let's pretend that you read an article that said that the average 25-year-old is only 4'3". Bam. You do your own test. You go out and get 30 25-year-olds, you measure them, and sure enough, their average is 4'3". But again, you could have got, some pygmies over in Africa where they're all really, really short. That could have been your sample size. So your data agreed with the stated data, therefore you do not reject the null, but you should have. Again, that's a type 2 error where you do not reject the null and you should have. And lastly, last time is it's not a researcher mistake. It's just that your data, your sample data is just behaving badly. And that happens, okay? But that's it for now. Okay, here's the last thing I want to go over in this video, and it's the t-test. The t-test is at the base of all things statistical. We use the t-test for everything. It's going to catapult us into the ANOVA. The ANOVA is simply doing a lot of t-tests at once. That's basically what an ANOVA is. But in a nutshell, we're going to be comparing sample means. That's what the t-test does. If you compare a sample mean to a population mean, that's a one sample t-test, which is very rare. You're rarely going to use that at all. You're not going to go up against a stated mean in real life. You might in this class, but not in real life. It's also called a one-sample t-test, also known as a dependent t-test. That's like the child, which is the sample, is challenging the parents, which is the dependent, right? That's a dependent t-test. All of our t-tests are going to be independent t-tests. That's where we're going to just compare a sample mean from one sample to another sample mean from another sample. Okay. And in a nutshell, how a t-test work is how the t-test works is it takes the means of the different groups and they subtract one another, so they find the difference between those two groups. They divide that difference by the number of standard errors, and if that number is greater than 2, then you get to say that yes, the sample means are significantly far apart from each other to be called significantly different. Therefore, you get to reject the null hypothesis. So that's how a t-test works in a nutshell. The t-table is a lot stranger than the z-table. And again, I'm not going to go into a lot of explanation here. I do have videos on how to look up t-table values. But the main thing between a z-test and a t-test is the degrees of freedom column. So the degrees of freedom, basically, it's a pretty difficult calculus term, but what it does is it controls for one variable and it lets the other variable go free, and I don't want to go into it right now, but that's what a t-test has. A t-test has degrees of freedom, and our ANOVA is going to have degrees of freedom. A one-sample t-test is the same as a dependent t-test. You'll notice that looks just like a z-score. And here's a one-sample test, t-test confidence interval. I don't think we're going to be doing much of that. But there's a two-test, right? Here's an independent sample t-test. It takes the sample from one mean, subtracts the other mean, and it takes what we call a pooled variance. And it will tell you, right, your t-score will be how many standard errors these means are away from each other, and if that is greater than the number 2, then you're probably going to have a significant difference, okay? But that's about it in a nutshell, and I hope you guys enjoyed this and are all caught up, because starting on Monday, we're going to go into the basic ANOVA, analysis of variance. So this is your teacher saying goodbye. Have a good weekend. I will be in touch.